Good morning, students. Today we will study about water potential. What is water potential and what role does it plays in the physiology of the plants? First of all, what is osmotic pressure? The maximum amount of pressure that can be developed in a solution separated from pure water by a semi-permeable membrane. This is the definition of osmotic pressure. How to understand what is osmotic pressure? All of you know that in osmosis, water or any solvent starts moving from its region of its higher concentration towards region of its lower concentration. So the amount of pressure that can be developed so as to stop this flow is known as osmotic pressure. Osmotic pressure is measured in pascals. Pascals, the unit of pressure, that is force of 1 Newton in an area of 1 meter square. Now the dependency of the osmotic pressure. The osmotic pressure of a solution largely depends upon the ratio between the number of solute and solvent particles present in a given solution. For example, we have taken molar solutions of sucrose and NaCl. The osmotic pressure of sucrose is approximately 22.4 atmosphere at 0 degree centigrade. However, sodium chloride has almost twice the osmotic pressure. Why this happens? Because all of you know that NaCl, being an electrolyte, ionic in nature, breaks up into Na plus and Cl minus ions. That is, the particle number is doubled in this case. So osmotic pressure depends upon the number of solute molecules in the solution. So we come to the derivation that OP is equal to CST. Now the term CST, C is the molar concentration of the solution, S is the solution constant and its value is always 0.082, and T is the absolute temperature, that is degree centigrade plus 273. Now all of you get aware that osmotic pressure is dependent upon the molar concentration of the solution. The term of osmotic pressure is more easily and, as you can say, literally more suitable term is solute potential. OP can be replaced by solute potential, but taken in a negative sense, negative charge. Negative solute potential. OP is equal to minus solute potential. That is, the solute potential is equal to osmotic pressure in magnitude, but it is opposite in sign and denoted by minus xi s and denoted by minus xi s, as you can see in the diagram. Cell wall, plasma membrane, and you can see the nucleus and the vacuole filled with the cell sap. Cell with the cell sap is turgid and exhibiting certain pressure on the cell wall. This pressure, outward pressure, is known as TP, that is turgor pressure. What it is called? Turgor pressure. Now again you are seeing inward arrows represented by WP, that is the plasma membrane. The layer is also, the cell wall is elastic and flexible and exhibiting an internal force in that which is equal to TP but opposite in direction, TP towards outside and WP towards inside. The wall pressure. What is WP? The wall pressure. So TP is equivalent to WP but opposite in the direction. Now we come to the what are the some of the importance of osmosis in plants. Why is osmosis so important in the metabolism of plants? First of all, osmosis is important in the absorption of water by the roots. Cell to cell movement of water and also the rigidity of the plant organs, that is the turgidity due to the in accompanying water molecules entering into the cell sap, providing it the rigidity and the turgidity. Leaves become turgid and expand due to their osmotic pressure. How this is possible? Endosmosis. Because of endosmosis, leaves become turgid. Growing points of roots remain turgid due to osmosis and are thus able to penetrate the soil particles and establishes itself in the soil. Resistance of plants to frost and drought. Highly turgid conditions in the plants resist itself from frost and drought. The wilting occurs when exosmosis occurs. What plant movements you have seen? The plants of Indian telegraph plant and the bursting of many fruits, sporangia occur due to osmosis. That is due to the entry of water, osmotic pressure increases and the fruit burst and the seeds are released. Opening and closing of stomata. Opening and closing of stomata also depends upon osmotic potential. So osmosis plays an important role as you will study more about these in essence of sap, water absorption, salt uptake, and further chapters how osmotic potential is playing in the role of these metabolic processes of plant. Simple water absorption. All of you know that the amount of water in the soil is more in the soil as compared to the root surface. So water first of all absorbed and then finally get absorbed into the root cells. From this roots it migrates upwards due to the difference in the diffusion pressure deficit. These all will be discussed in the next classes, how this change in DPD results in the movement upward lifting of water. So much heighted plants gets water from the roots against the gravitational force. This all will be discussed. Now, a gist of the importance of osmosis in plants is that in role in water absorption, cell to cell movement of water, maintaining the rigidity and turgidity of plant organs, protection of root growing points, resistance of plants from frost and drought, various plant movements, opening and closing of stomata. These are some of the importance of osmosis in plants. Now we come to the term what is TP or turgor pressure. Actual pressure exerted by the protoplasm against the cell wall, as you have seen in the previous diagram I have shown you. TP, outward pressure by the protoplasm. This is called TP, turgor pressure. What it is called? Turgor pressure. And towards this turgor pressure, being cell wall rigid and elastic, so it exerts an equal and opposite pressure against the expanding protoplasm, and it is called WP, that is wall pressure, and TP is always equal to WP. Turgor pressure at a given time, TP is equal to WP. So all of you now knew about what is osmotic pressure, what is turgor pressure, and what is wall pressure. Now we come to the definition of diffusion pressure deficit. What does the term denote? Diffusion pressure deficit, DPD, or suction pressure given by Renner, and nowadays we use water potential in place of DPD but in a negative sign. So what it is? The pressure exerted by the diffusing particles is known as diffusion pressure, and this pressure will be proportional to the concentration of the diffusing particles. We know pure water has maximum diffusion pressure, and if a solute is dissolved in the pure water, the resulting solution attain less diffusion pressure than in the pure solvent. So, the amount by which the diffusion pressure of a solution is lower than that of its pure solvent is known as its DPD, diffusion pressure deficit, which is equal to OP minus WP, that is osmotic potential minus wall pressure, and all of you knew that wall pressure is equal to turgor pressure, so DPD will be OP minus TP. What it will be? DPD will be equal to OP minus TP. Now we come to the concept of water potential. What is water potential? What is water potential? The concept of water potential, that is the difference between the free energy of water molecules in a pure water and that when compared to any other system. This is called water potential, denoted by Xi. The water potential is measured in bars. A bar is a pressure unit. The components. Now we come to the components of water potential. Xi m, Xi s, Xi p. The components of water potential are metric potential, solute potential, and pressure potential. What it is? Xi m, metric potential, Xi s, solute potential, and Xi p, pressure potential. Now, what is Xi m? What is Xi s? And what is Xi p? What is Xi m? Metric potential. Metric potential. The word metric is a term used for surface of hydrophilic colloids such as clay particles, certain cell wall polysaccharides, proteins, starch, and to which the water molecules are adsorbed. Usually the hydrophilic surfaces of clays, proteins, and microstructures of cell walls have large unbalanced negative charges with which the positive ends of water molecules get attached. That is, adsorption of water molecules on the surface of hydrophilic colloids lose certain amount of energy, and this result in the build of metric potential Xi m. xi m, it has also a negative value, and the value of xi m is so less that the contribution of metric potential is negligible in the final water potential of the plant cells and tissues. So it is neglected in the equation, and we come to the final equation of water potential as xi p plus xi s instead of xi m xi p plus xi s, because we neglect xi m since its value is too negligible. Now all of you knew about metric potential. Now we come to the term solute potential. Solute, whatever molecules dissolved in a solution, a solvent to form a solution, that is solute. Solute potential is also known as osmotic, what it is called? Osmotic Osmotic potential. It is defined as the amount by which the water potential is reduced as a result of the pressure of the solute. Solute potential or osmotic potential are always taken in negative values. Now comes pressure potential. Metric potential, solute potential, and then comes the term pressure potential. All of you know plant cell wall is elastic and it exerts a pressure on the cellular contents. As a result of inward wall pressure, hydrostatic pressure is developed in the vacuole termed as turgor pressure, and the pressure potential is always positive and operates in the plant cells as wall pressure and turgor pressure. So this is all about DPD and water potential, and water potential is nothing but DPD taken in a negative sign. Now I will discuss you about what are the differences between DPD and water potential. DPD, diffusion pressure deficit, also known as suction pressure, and water potential is the chemical potential of water, which is equivalent to DPD with a negative sign. DPD is abbreviated as DPD, whereas the symbol for the water potential is by a Greek letter xi, and DPD is the difference in diffusion pressure between a solution and pure solvent, whereas the water potential is the difference between the free energy of water molecules in pure water and in solution. DPD is measured in atmosphere, whereas the water potential is measured in bars. The direction of water movement is from low DPD towards high DPD, and the direction of water movement is energetically downhill from high water potential to the low water potential. This should be very clear to you that water always moves from high potential to low potential, and the direction of water from in terms of DPD is from low DPD region, where the DPD is lower, to the area where DPD is higher. Low DPD, that is water amount is more here. So water will move from low DPD area towards high DPD. Diffusion pressure deficit is equal to OP minus TP, whereas the water potential is equal to metric potential plus solute potential plus pressure potential. This is all about the water potential and DPD, and in the next lecture we will study about the osmotic relations of the cell in hypertonic, hypotonic and isotonic solutions. Thank you.